Yes, students, our next topic is the electronic structure and properties of complexes with the help of the CFT. Now, the electronic configuration of the complexes, it is going to depend upon the crystal field splitting. Now, the magnitude of the crystal field splitting, it depends upon the nature of the light. The ligands, they cause the splitting of the d orbitals into two set of uh, orbitals. One, it is T2G, which has got the lower energy, and EG, which has got the higher energy in case of the octahedral complexes. Whereas in case of tetrahedral complexes, the T2G set of orbitals, they will have the higher energy, and the PG set of orbitals, sorry, T orbitals will have the higher energy, and the E set of orbital will have the lower energy. From the Hund's rule of maximum multiplicity, we come to know that the electrons will first get singly filled in a given subshell, and later on the pairing will begin. Now the term pairing here, it will be affected by the splitting of the d orbitals, that is the extent of splitting, whether the splitting cost is small or it is less, that is the energy difference to maintain the stability of the complex is large or small, right? So the electronic structure, that is the electronic configuration, right, which is going to affect the property of the complex, will depend upon the crystal field splitting. Or we can see here that the electronic configuration of complex depends upon magnitude of crystal field splitting. That is, we can simply write it as delta, and if it is delta O, it will be octahedral complex, and this delta T, it will be for tetrahedral complex. Now, students, if we have got on the central metal ion, right, if it has got D1, that means it has got single electron in the d orbital. In that case, right, so we will just have this 3, this is 4, and this is 5, that is the 5 d orbitals, which will still degenerate, but after the approach of the ligand, it gets split up, right, and we get the two set of orbitals, T2G and EG. This I am drawing for the octahedral complex. That's why the crystal field splitting here is shown as the delta naught. Right, students? So here for the tetrahedral complex, right? So you know that this, the energy which is increased is by 3/5 of delta naught. That means if this splitting will be less, this energy which is being raised up will be also less, right? And if this splitting will be more, so its 3/5 part, that much energy to maintain the average d subshell d orbital's energy, it will be raised up. So students, when we have only one electron in the d orbital, in that case, it will first occupy the lower energy. So that time the d1, this is the electronic configuration of metal ion, and that of the complex, it will be written as T2G1 and Pg0, right? So electronic configuration of complex is here T2G1 and Pg0. Now students, when we have, similarly we can do for D2, and I am doing here for D3. Here also it will be same, in the same pattern. That is, here we will just show first 5d orbitals. This is 3/5 part energy has been risen up. This is 2/5 part which has been lowered. This is delta naught. Here we have got 3 T2G orbital, here it is 2 EG orbitals. Now here since it is 3, it's okay, we will fill 1 electron in each orbital, right? So here the configuration of the metal ion is D3, right? Whereas that of the complex, it is how much? It is T2G3 and Pg0, right? Now this was for when we are writing for 1, 2 and 3. But what will be the configuration when we are writing for the D4, right students? So that means that if we have D4 and metal ion has got 4d electrons, at that time this is 1, 2, 3, 4, 5. You can draw the blocks also here. I am drawing the circle, you can draw the block also. So 3/5 energy risen up, 2/5 lower down. This is delta naught, crystal field splitting. Here we have got 2 EG orbitals. This is 3 P2G orbitals here. Now we have got 4 electrons. Students, just look here carefully. So this is T2G, right? This is T2G and this is EG set of orbitals. Students, whenever you are drawing the diagram of CFT, you will always mention the set of orbitals, which one is T2G and EG, and you will denote the crystal field splitting also. So here we have got 4 electrons. So 1, 2 and 3. Right. Now 3 electrons are filled up. What about the 4th electron? We can have 2 cases here. Right. The first case, what we can have, that the 4th electron jumps up. This is case 1, case A, right? If this is so, that time the complex configuration will be T2G3 and EG1. Now we can have second case also, right? This is case 2. So here we have 5d orbitals. This is delta naught. To get the thing clear, just by seeing the diagram only, you can just predict what will happen here and why it will take place. So here we have got 4 electrons here. So the case 2 is that 1, 2, 3. And the second, what can happen, that instead of going to EG, it will just get paired up. So students, that time the configuration of the complex will be T2G4 and EG0. Right? Let me check. Is it visible to you? Yes. So it is T2G4 EG0. So students, when we have 4 electrons in d orbitals, that time we get 2 cases, case A and case B. In case A, that the T2G orbitals will get single filled up and the 4th electron will go to the EG orbital. That time we will get the configuration T2G3 and EG1. And case 2 is that if the 4th electron, instead of going to EG, it will just get paired up, right? And that time we will have the configuration T2G4 and EG0. Now, can you tell me that why it will happen so? You can just see here the figure, right? The 2 cases crystal field splitting diagram you can see here. You can easily point out the difference, right? So what's the difference between the 2 here? If you see that both have 4d orbitals, both have got the T2G set of orbitals at the bottom and 2 orbitals of EG at the top, right? The difference is that if you just compare the splitting, the crystal field splitting, the magnitude of crystal field splitting, here you can see that the magnitude of crystal field splitting is less, and students, here the magnitude of crystal field splitting compared to the first case is it is more, right? It is definitely going to affect the electronic configuration of the complex, right students? So I'm just rubbing the board here. The diagram are still at the on the board, right? So the case A. Now student here, the delta naught, right? Now students, one thing is there, whenever the electrons are paired up in an orbital, it is always at the cost of an energy. There also energy is required and that energy is called pairing energy, right? So to get the electron paired up in a given orbital or in a particular orbital, energy is required and that energy is called pairing energy. Now student, here you can see that the electron has preferred to jump up to EG orbital. It means that the energy, that is the crystal field splitting, that is delta naught, is less than the P, that is the pairing energy. Students, here P stands for the pairing energy, that is the energy required to get the electrons paired up, right? So here the pairing energy is more, therefore the electron will jump up to the EG set of orbital and there it will get filled up, right? So here the splitting, the magnitude of splitting is less, and that is the characteristic of weak field ligand. So weak field ligand cause the less magnitude of crystal field splitting, right? So the magnitude of splitting, that is crystal field splitting here, right? This is here crystal field splitting CF, that is, student will write it complete. Crystal field splitting is less and that is caused by the weak field line, right? So here, if it is weak field, that at that time we will get, so the pairing will not be done, right? So we will get number of unpaired electron more, so it will be forming high spin complex, right? So I'm rubbing the case 1 from here. Now the case B, here you can see that delta naught is greater than the magnitude of delta naught is greater than P. So here it is the strong P ligand. So it will be caused by the strong field ligand. The magnitude of crystal field splitting will be more than the pairing energy, right? And hence the pairing will take place and a low spin complex will be formed, right? So the complex which will have a strong field ligand, they mainly form the low spin complex, and which will have the weak field ligand will form the high spin complex, right students? So these are definitely, the electronic structure will be affected by the nature of the ligand, right? And that is going to affect the property of the complex, which is because it is going to affect the number of the unpaired electron. As a result, the type of the complex is going to change, the high spin and the low spin complexes. It will definitely affect the color as well as the magnetic property of the complex.